Welcome to our explainer, where today we're tackling the absolute essentials of electrical engineering standards in Saudi Arabia. We're going to break down these complex codes and turn them into a real-world practical inspection tool that you can use to get your projects safe, compliant, and approved.
Okay, so here's how we're going to walk through this. We're following the logical flow of any project, starting with the legal rules you can't break, moving into design, then protection, and finally, getting that all-important sign-off from the inspector.
All right, first up, let's lay down the law. I mean, literally. These are the absolute, non-negotiable rules that form the foundation for every single electrical project in the kingdom. There's no way around them.
Now this is so important to get right. You've got to understand the hierarchy. On the left, those are the local codes, Saudi Building Code, SEC, Aramco. These are mandatory. The ones on the right, like NEC and IEC, they're great, but they are for reference only. Your entire QA/QC process has to be built around the local codes, period.
So let me make this crystal clear. If you ever find a conflict, maybe something the NEC allows but the Saudi Electrical Code says no to, guess what? The SEC wins every single time, no exceptions. This is one of the very first things an inspector is going to check in your design basis report.
Okay, so with that hierarchy in mind, let's look at the actual system you are required, by law, to use. And I want to stress that this is not a design choice. It is a legal mandate from the SEC and SBC.
These are the numbers that have to be on your single line diagram. No questions asked. We're talking 400/230 volts, 3-phase, 4-wire. The frequency has to be 60 Hz. Using 50 Hz equipment is a huge and surprisingly common mistake, so watch out for that. And for safety, it has to be a TNS earthing system. That means your neutral and your earth conductors stay separate all the way through the system.
All right, so now that we have the ground rules, let's see how they actually affect the next stage, designing and sizing your system. And this isn't just about plugging numbers into a calculator. It's about engineering for the very real, very hot conditions you find in Saudi Arabia. You know, one of the biggest mistakes that leads to oversized and super expensive systems is sizing for the total connected load. The codes don't actually ask for that. What they demand is that you calculate the maximum demand. You do that by applying a diversity factor. Because, let's be realistic, not everything is going to be on at full blast at the exact same time.
And this is where things get really interesting. Because the local climate has a massive impact. You're not designing for a cool climate here. You have to size your transformers to survive a constant ambient temperature of 50 degrees Celsius. Your standard off-the-shelf thermal margins, they just won't cut it.
So, to handle that brutal heat and make sure the system is reliable, the SEC and SBC codes give you a clear instruction. You take your calculated maximum demand and you multiply it by a safety factor of at least 1.25. That number gives you the minimum kVA for your transformer, and you better believe the inspector will check that calculation against your transformer's datasheet.
And that same thinking, designing for heat, applies directly to our cables. You can't just look at a manufacturer's catalog and pick a cable based on its amp rating. No way! You have to derate it, reducing its capacity to account for both the high ambient temperature and the heat generated when you group a bunch of cables together.
And here it is, the exact formula, pulled straight from the standards. The rating you need, that's IZEL, has to be bigger than your design current divided by all your derating factors. This isn't just theory. Your QA/QC inspector will use this exact formula to audit your cable schedules. Your paperwork has to be perfect.
So, we've sized a system to handle the load and the heat. Now we have to switch our focus to protection. We need to be sure it works perfectly day to day, but even more importantly, we need to know it's going to fail safely when things go wrong.
The SEC is incredibly strict about voltage drop, and for good reason. It protects motors and sensitive electronics. The rules are simple and firm. You can't have more than a 3% drop on your main feeder, and from the source all the way to the farthest outlet, the total drop can't be more than 5%. Your voltage drop calculation sheets are a critical part of your submission package.
Now for a huge safety check that honestly gets overlooked way too often. We all obsessed over the amp rating of a circuit breaker, right? But that's only half the picture. The really critical question is about its short circuit rating.
Look, this is a life or death detail. On the left, someone chose a breaker with the right amperage, but they ignored its interrupting capacity, its Ka rating. The system's fault level was higher, and the result is a bomb, a catastrophic failure. On the right, the correct breaker handles the massive fault current and clears it safely,
The only place you can get this Ka value is from your approved short circuit calculation report.
Okay, we're at the finish line. Let's talk about the final checks that happen right before the system gets energized. This is where inspectors scrutinize earthing for life safety and power factor for the utility company.
So imagine this. It's final inspection day. The engineer comes out, connects their earth resistance tester to your system, and gets a reading of 6 ohms. That's it. Project fails on the spot. It's considered unsafe. A reading that high means the system can't get rid of a fault current safely, and that creates a deadly shock risk.
Now let's flip that. You've installed the earthing grid exactly as designed. The test is done again. The new reading? 1.2 ohms. Perfect. That is a safe, compliant value that will be accepted by SEC and Aramco inspectors without any issues. And your signed earth resistance test report is the proof you need.
The utility company has its own checks too, and this one can hit you in the wallet. A power factor of 0.8 is inefficient, and it puts you right in the SEC penalty zone. That means you're going to pay more on your electricity bills. But by installing the right capacitor bank, you can correct it to a compliant and efficient 0.95.
So, when you put it all together, what's the big takeaway? It's that by following these steps, you're not just making a system that works. You're creating a system that's safe, efficient, and, most importantly, ready for official approval. Every single step we talked about can be verified with the QA/QC check that links right back to your approved construction documents. And that really just leaves us with one final question for you to think about. When you look at your own projects, is every single calculation, every data sheet, every test report, and every drawing ready to pass this kind